Hey everybody, and welcome to Algo Expert. In this video, we will be going over the middle node problem. So in this problem, we've been given a linked list, such as this one here, and we need to return the middle node. So in this case, the middle node is going to be 3 because there are 2 nodes to the left and 2 nodes to the right. So we return the middle node of 3. It's worth noting that we return the linked list node, not the value. So we do end up getting essentially an entire linked list returned. Additionally, if we had a linked list with an even number of nodes, so for example, if we got rid of 6 here, then in this case, we don't really have a middle node. We have 7 and we have 3. They are both in the middle, and we want to always return the last of these middle nodes, so we would still return 3. Okay, so how can we go about trying to solve this problem? Well, we need to think about what does it actually mean to be the middle node? Well, first of all, it means there are the same number of nodes to the left and to the right of that middle node, assuming there's an odd number of nodes, or it might be off by 1 if there's an even number of nodes. Additionally, it means that this node is at the index of the length divided by 2. So if we say the length of this linked list is going to be 5, and we divide it by 2 because it's in the middle, we would end up getting 2.5, and if we floor that value, we would end up getting the index of this node, which is 2. So this is index 0, index 1, and index 2 here. And this is actually still going to be true for the even length linked list. So if we did not have the 6 once again, then this would end up being 4 divided by 2, which is simply 2. So we would still end up at index 2, which of course is what we want. Okay, so let's erase all this and see if we can figure out how exactly to create this solution. So we know we need the length of the linked list, but we're not given a length. So we can go ahead and just calculate that length ourselves. So what we're going to do is just iterate through the list until we get to the end and increment some counter. So we can say we have a count, and we can simply set this to be 0, and then we can iterate through the list. So we start on this first index, and when we get to that first index, we increment our count to be 1, and then we get to the next number, which is the 7, and we can increment our count to be 2. And then, of course, we would get to the 3. We could increment our count to be 3. We would then get to the 5, and we could increment the count to be 4. And then we would get to the 6, and we would increment the count to be 5. And at this point, our count is the length of the linked list. And now we can very easily calculate the index of our middle node. So we already determined that that index is going to equal the count divided by 2, and we need to floor this value. And this is for the case of the odd length linked list. We want the lower value to get the middle index because of zero-based indexing. So in this case, the index is going to be 2. And now we can just simply iterate through the linked list. So we start on the 2, and at this point we can say we are at index 0, and then we get to the 7, we're at index 1, and then we get to the 3, and we're at index 2, and this matches the index we are looking for, so we can simply return this value, and now we have the solution. And time complexity-wise, this is going to run in big O of n time because of the fact that we have to iterate through the entire linked list. We do this twice, once for the count to get the length of the linked list, and a second time to find the middle index. But because these aren't nested in any way, it is simply O of n, with n being the number of elements. And then for space, we can simply call this O of 1, because any extra space we use is not going to scale with the size of the linked list, because all we need is this count, our index, and references to whatever current nodes we are at when we are iterating through the list. Okay, so that's going to do it for this first solution, but there's actually another solution I want to show to this problem. So let's clear off all of these markings and solve this same problem in another way. So when we look at linked list problems, there are a few patterns that we tend to use, and one of those patterns is to have multiple pointers, and that is going to be a pattern that is going to be useful here. So the intuition behind this second solution is that if we had 2 different pointers, so let's say we have the first one here, and we can have a second one here as well. And now we can iterate with both of these pointers. So for example, we can move this 2 to the 7, and then we would end up eventually moving the 7 to the 3. And we want to be able to stop when this pointer gets on the 3 because that is the middle node. So then what we can do is we can use the second pointer to know when we need to stop. So what I'm going to do is I'm going to put these back, and what we can do is move the second pointer at twice the speed so that when it gets to the end of the list, the first pointer is going to be in the middle. So on the first iteration, we're going to take the blue pointer and move it to the 7 because we increment it by 1, and then we can take this green pointer and we can move it to the 3 because we increment it by 2. And then on the second iteration, we will move the blue pointer to the 3, and we will move the green pointer to the 6. So now at this point, the green pointer is at the end. So we know it's at the end because the 6 has no next pointer. So whenever we get to that point of it being at the end, we know that the blue pointer must be in the middle because the middle is halfway to the end, and this one is moving at twice the speed of this one, so we can go ahead and return 3. And now whenever we use a solution like this, we need to make sure it does work for odd and even length cases. So in the odd length case, essentially what we're doing is we stop when this next pointer does not exist. Well, let's try the same thing, but let's go ahead and do it without the 6, so we have an even length list. So in this case, we can take the blue pointer and we can move it to the 7, and then we can take the green pointer and increment it by 2 to move it to the 3. Next, we would take the blue pointer and we would increment it to the 3, and the green pointer would go from its current value to cur.next.next, which is now at null. And at this point, we can stop because the green pointer is pointing to null. And then again, we would return this value of 3, which is the second of the middle nodes. So essentially what this means is that in the even length case, we will stop when the green pointer hits null, and in the odd length case, we will stop when the green pointer's .next value is null. So to handle both cases, we are going to stop when the green pointer, so our faster pointer, is either pointing to a value that has no next value, or it's pointing to null itself. And now time complexity wise, this solution is also going to be big O of n time, because we are simply iterating through this linked list one time. We are using 2 pointers, but it is just one iteration. And then space complexity is again going to be O of 1 space, because the only space we use is for these 2 different pointers. We are not creating any space in memory that is going to scale with the size of the linked list. And with that, that's actually going to do it for the conceptual overview of this problem. Let's move over to the code editor and do the code walkthrough. Okay, so now we are here in the code editor, and we can see we have our function middle node, and it takes in the linked list. So for the first solution, the first thing we need to do is we need to first of all get the length of the linked list so we can count all of the nodes. So we can say count is initially going to be equal to 0, and then we can also create a current node reference to be equal to the head of the linked list. And now we're just going to iterate through the entire linked list. So we can say while current node is not none. So while we still have a current node, we are going to increment the count. So we can say count plus equals 1, and we are going to move the current node to the next value. So we can say current node is going to be equal to current node dot next. Okay, so now count is going to be equal to the length of the linked list. And now we can iterate through the linked list until we get to half of the count. So let's create another current pointer. So we can say middle node, which is going to be our output, is going to be equal to the linked list. And now we want to iterate until we get to count. So we can say for in range, and we will do count, but we need to also divide by 2, and we can use this double division for integer division. So we can do divide by 2 to get halfway through the count or halfway through the length. And now in each of these iterations, all we're going to do is say middle node is going to equal middle node dot next. So again, this is just iterating through the linked list, but this time iterating through half of it. And now our middle node is going to be the middle node, what we want to return. So we can simply return the middle node. And with that, that is a completed solution to the problem. So let's come up here and add our time complexity. So again, this is going to run in big O of n time, as well as it will run in O of 1 space. So we use in time twice here. So once to iterate through the entire linked list, this is an O of n operation, as well as iterating through half of the linked list is also O of n, because this will scale linearly with how large the linked list is, but these are not nested within each other, so it is just O of n time, and we do not use any extra space besides our count and current node and middle node, so we just have O of 1 space. Okay, so that is the first solution, but now let's implement the second one. So I will go ahead and comment this out, and let's come down below here, and I will also make a little bit more space so that we can scroll down a bit. And now we are going to create our new middle node function. So we can say def middle node, and this again is going to take in the linked list. And now this function is going to use the two-pointer approach. So we will have the slow pointer and the faster pointer. So we can say slow node is going to be equal to the linked list, and fast node is also going to be equal to the linked list. And like we saw in the conceptual overview, we are going to be finished when the fast node is either null itself or its next pointer is null. So we can say while fast node is not none, and fast node.next is not none. And while this is true, we are going to update both slow node and fast node. So slow node is going to equal slow node.next, but fast node is going to move 2 at a time. So fast node will equal fast node.next. And we do know this won't throw an error because we know that fast node.next is not none. So this could potentially be none, but it will not throw an error because we know at least fast node.next does exist. And now when we finish this while loop, so once we reached the end with the fast node, we know slow node is at the middle, so we can simply return the slow node. And that's going to do it for this solution as well. So this one also is going to run in big O of in time, as well as it is going to be big O of 1 space. And again, this one is O of n time because of this while loop that is going to scale with the size of the linked list linearly. So essentially this just iterates through half of the linked list, but that is still O of n, and then we use O of 1 space. The only space we use is to create slow node and fast node, which are not going to scale with the size of the linked list. And with that, that is going to be the end of this video. I hope you found it helpful, and I'll see you in the next one.